So what was lacking in early atomic theories was some way to test whether or not atoms existed. Atoms needed to have some sort of a property that connected to the everyday world so that observations could be made and connected with the conclusion that all matter is made of atoms. Now, no one did that for quite a long time, for millennia, until John Dalton came along. He was a Quaker school teacher in the early 1800s, and he was actually more interested in a problem in meteorology than he was interested in chemistry. He wanted to explain why wet air was lighter than dry air. And in trying to find an explanation to that problem, he stumbled on atomic theory. And he was able to successfully explain that, and we're going to come back to that when we study gases later. But he started out by saying the same thing that Democritus said. Everything is made out of atoms, tiny indestructible particles. And here's what's different from Democritus. He said that what makes atoms of one element different from another element is that they have different masses. So, for example, if you've got a carbon atom, C, it has a mass of about 12 atomic mass units. We're going to define atomic mass units later. They're very tiny masses. But let's say 12 units, that weighs 12. And if you look at oxygen, that weighs 16U. And if you were to look at, say, a hydrogen atom, little tiny circle there, that weighs 1U. That turned out to be the lowest mass atom that there was. So he put that as 1 unit on his scale. Carbon atom would weigh 12 times as much as a hydrogen atom, and an oxygen atom would weigh 16 times as much. And we'll see in a little bit, in another lesson actually, where he got those atomic weights. He built up a whole scale of them. Now, something else he said was, since the atoms are indestructible, reactions are just rearrangements of atoms. And remember, we spent some time talking about this in the fundamentals lesson. We looked at how you don't create or destroy atoms during a reaction. You've got to have the reaction balanced. So there's some experimental support. This explains the law of conservation of mass. Now let's remind ourselves what the law of conservation of mass is. Again, we hit this in the fundamentals lesson. It says that before and after a chemical change, there's no change in mass. You don't create or destroy mass during a chemical reaction. And that makes perfect sense if you're just restacking the atoms, reconnecting them, rearranging them in a chemical change, then you're not going to change the mass, because the atoms have fixed masses, and if there are no atoms going away or no new atoms coming, the mass will stay constant. So that's the experimental basis for this. Here's the big thing, though. Compounds are made of molecules. That contain characteristic numbers of atoms. Okay, now that means that a specific molecule will have a certain number of atoms of each type. Let's look at two compounds of carbon and oxygen here. I've got carbon monoxide here, CO, and it's got one carbon atom hooked to one oxygen atom. Now, if carbon weighs 12 and oxygen weighs 16, the whole thing together will weigh 28. So we ought to be able to explain why carbon monoxide always has 42.88% carbon. If you take 12 divided by 28 times 100%, you'll get the experimental percentage. So that's pretty powerful. If you want to get the experimental percentage of oxygen, take the weight of the oxygen divided by the weight of the compound. So this 28 is the mass of the CO. It's the total CO mass. And this is just the carbon, and this is just the oxygen. So if you want the oxygen percent, you could take the weight of the oxygen divided by the total times 100%. You should get something very close to your experimental percentage of oxygen. So these numbers are easy to measure experimentally. If you weighed the amount of carbon you had and then you burned it and made carbon monoxide and weighed that, you could experimentally get this. So this is very powerful evidence for the existence of atoms, and it's evidence for the whole scheme about atoms having distinctive masses. Now, if you look at carbon dioxide, it's got different percentages of carbon and oxygen. These are characteristic of carbon dioxide. Wherever you take carbon dioxide from, there's 27.29% carbon and 72.71% oxygen. If you've got some carbon dioxide that doesn't have those percentages, it isn't pure carbon dioxide. It must have impurities in it. So that's a way you can detect impurities. If your percentages are not what they're supposed to be for this, it must be impure. But anytime you have pure carbon dioxide, whatever the source, whether it's from Earth or from space, it will always have the same percentage composition. In fact, that's a law. It says it's the law of fixed composition, and it says that a compound will always have fixed percentages of elements in it that are characteristic. Now, can we calculate what these experimental percentages are going to be from Dalton's scheme? Sure. There's a carbon in there that weighs 12, and there are two oxygens in there that weigh 16 apiece. So if I wanted to calculate this percentage of carbon, it would be the weight of the carbon that's in there divided by the total weight. 16 and 16 is 32, plus 12 is 44. If you punch that into your calculator, you'll get about what I got there. Try it again for the oxygen. If you want to get the percentage of oxygen that's in the compound with Dalton's atomic theory, you would say, what's the total weight of the oxygen that's in there? 16 and 16 is 32. And the whole thing together weighs 44 times 100% to make it into a percentage. Should give you the number that you have up there if Dalton's explanation here is correct. It looks pretty close. Now, another thing you can look at is the mass ratio of the elements that are in here. When you say something is 42.88% carbon, that means that there are 42.88 grams of carbon in every 100 grams of compound. So let's look at these as though they're masses that you would have of these elements in 100 grams of compound. And take the ratio. Take the oxygen to carbon ratio. 57.12 divided by 42.88 gives you a number, 1.33. That number is always the same for any sample of carbon monoxide. It's characteristic. It's like a fingerprint of carbon monoxide, 1.33. That's called the law of definite proportions. It says every compound has got a fixed ratio of elements in it. And again, the explanation is the same thing. You could figure out this ratio here from the fact that there's one carbon in there and one oxygen. We're going to do that a little later. Let's not do that now, but we could calculate this number just as easily as we calculated these two from the molecule. What if I do the same thing for the carbon dioxide? Here there's 72.71 grams of oxygen in 100 grams of compound and 27.29 grams of carbon in 100 grams. And when you form the ratio, the definite proportion, you get 2.66. So that's a characteristic of carbon dioxide, which can be explained by looking at the carbon dioxide molecule there. Now there's another law that they mention in your textbook, and it's called the law of multiple proportions. And that is basically, you'll see something, you might notice something about these two numbers. This number is exactly twice that number. So if you take 2.66, the oxygen to carbon ratio in carbon dioxide, and you divide it by 1.33, the oxygen to carbon ratio in carbon monoxide, you get exactly 2. And Dalton's explanation for this pattern is there are twice as many oxygen atoms per carbon in carbon dioxide than there are in carbon monoxide. So you can see that subscript there showing up in numbers that you've experimentally determined. So this is something that we're going to come back to, and we'll simplify this a little bit by introducing the concept of moles. Right now this might seem a little bit opaque to you, but what's important, I think, here is to see that all of these numbers that you can get experimentally can be explained with an atomic model, with Dalton's atomic model. Now, let's go back and look at the postulates, they call them, the things that Dalton assumed in his theory. Do we still believe all this stuff? Mostly, yes, we do, but there are some little fine points that Dalton didn't know about that we do. He said what makes atoms of different elements different is that they have different masses. So the mass is kind of a characteristic, he said, of an element. We're going to find out, surprisingly enough, that different atoms of the same element can vary a little bit in mass. So this isn't quite true, it's almost true. What really makes one atom different from another is has to do with the positive charge that you can find on the nucleus of the atom. Every atom has a unique positive charge on its nucleus. We call that the atomic number, and you can see it as that number on periodic tables. We'll come back to that within this lesson a little bit later. So this isn't quite right. We don't quite believe this anymore. It's almost right, though. This is still fine. We still know that you don't get changes of masses in chemical reactions, but you can get them in nuclear reactions. If you get a change in mass, if mass can be converted into energy, which has no mass, and if something like that happens, you don't really have a chemical reaction, you have a nuclear reaction. So this is still good. How about this? Compounds are made of molecules that contain a characteristic number of atoms. Yes, that's still fine. What about the idea that atoms are indestructible? Well, we know that's not quite right now. We are going to see, in fact, in the next video, that you can smash an atom. You can take little pieces off of it. So they are not quite indestructible. So those are some things about Dalton's theory that are not quite right.